My name is Blake Mizerany, and this is on distributed failures. How many of you work with, Pedro asked this yesterday and I saw the hand count, but I'm going to ask again. How many of you work with distributed systems right now? Okay, good. So for those of you that don't, if you have any questions or need to slow me down, you can raise your hands and ask a question. So this is, I'm B. Mizerany on just about everything, GitHub, Twitter, so forth, so on. Many of you may know me from the Sinatra project that I started in 2007. And I work at Heroku, and all of you obviously know about Heroku now because you were all here for Pedro's talk yesterday, I'm sure. And we are a platform as a service. Let me break that down for you. We are a platform as a service. We are not a platform you service. So we run all of the things for you. So don't be confused with this. We manage for you Ruby, Java, Node.js, Clojure, Python, Scala, thousands of servers, over 500,000 apps, billions of page views, and a full-on Postgres database service. We run all of the things. So really, we do. Even all the de facto Facebook apps now are run on, or the default for Facebook apps are now on Heroku. But this was a long road. And the reason I went through all of that briefly was because I wanted you to know that we deal with a lot of problems in distributed systems, right? In order to manage all of the things I just described, there is a lot of complicated things going on to make all of those things work together. And for us to be able to serve billions of page views and manage thousands of servers for you. But this also took many iterations. We built many different services. Pedro went over this yesterday. You saw how we broke down. We had one monolithic thing that we were working with, and we broke it into smaller and smaller pieces over time. And as you do these things over time, there's different problems come about, and in order to make that happen. So I want to go over with you the evolution of a distributed system. Or I have the acronym that I use, C3T. So in a very particular order, that is communicate, coordinate, consolidate, and then tolerate. So let me explain what I mean by communicate. When I say communicate, this is all the things that are happening in the distributed, in all the different servers and all the little components. As they're performing each of their individual functions, they're trying to communicate with each other to let each other know where they are at any given time. And that be state, location, IP addresses, just any kind of information that another component may need. They're trying to communicate that. So this is an older kind of sketch of what Heroku's architecture looks like, and it still is pretty valid today of how it looks. So you can see here we have Nginx running all of your requests coming in. So all of your web requests that come in go through Nginx, then go through Varnish. On the new Cedar stack, we no longer use Nginx, but this is still applicable to what I'm talking about. And so then it would go through Varnish and Hermes, and then to your dynos. And off to the side, we had other little ancillary mechanisms like Git, and we had the API, and these were all these endpoints for you to manipulate your applications on Heroku. So things that we would normally communicate in this scenario are we have a new Hermes. And what I mean by Hermes is how many of you know we used to call the dyno mesh, and today we call the dyno manifold. We like coming up with fun names for these things. So in order for the system to be able to coordinate, it had to communicate. So whenever a new Hermes would come up, we'd have to tell Nginx about it. And whenever there was a new dyno, we'd have to tell Hermes about it so that it could begin routing traffic to the new dyno. Because you're paying for that dyno, you want traffic going to it in real time, right? So the natural start for us was to use RabbitMQ. This was an easy way for us to get started when we were trying to communicate all this information. And so we would broadcast things. We would say, oh, I'm up over here, or I'm down, or I'm in this state, or I'm in that state. And so this is normally the natural thing you do. You're just telling other people about what it is this component is doing. So this component's saying, I'm alive, and he's pinging into a ping server, or he's telling someone else that, hey, I've got these dynos I'm managing. I've got these dynos I'm managing, but he's continually doing this. So this gets really, really expensive, right? There's a big complexity problem here. The more servers and components we add, the more messages going through the system. And it's kind of almost exponential, right? Like the more we add, it just gets worse and worse and worse. So then we need to, it's a really sad problem. I'm going to tell you how we fixed it. Just hold on. So we had to coordinate So let me talk about coordination now. So when we talk about coordination, okay, so I said that I'm down, or I lost a dyno, or the dyno went down, or this server's gone down, or this server's gone up. We need to be able to tell someone about that, and we need to coordinate efforts so that whenever you hit Heroku create, we asynchronously do many things for you at once. One of those is create a database for you. The other is start the dyno for you. The other is start a slug for you, right? There's a lot of different things that get set up all at once, and then once it's all done, it comes back and then says, okay, you're good to go. And so once you're good, that means that everything's ready for you to push your code up. And when you push your code up, we then do a couple things, and then we divvy the work up and then spread it throughout the grid. So in order to get that information around, we need to be able to coordinate state. We need to say, okay, the database is done, this is done, that is done, and to know what state we're in. Are we partially complete? Are we 100% complete? I don't want to return just, I don't want to return just a few things and say, well, we created your database, but you can't push the slug. That's useless. We need to know that everything is ready for you to go. So the state of all the things is we need to be able to get this information. And so broadcasting isn't always the best solution. So one of the things we would do is, and let me explain why. Because when we needed to know what the state of the system was, we would broadcast the message out. We would ask the entire system a question via RabbitMQ. Who are you running? Where are these dynos for this application? And then we would wait, and then they would reply back to us, right? And then because we were trying to get real-time information. And so the problem with this is what you wind up with is an ad hoc solutions. You wind up creating all these like little modules and components and trying to, with timeouts and all sorts of other stuff, to try and coordinate this information and try and judge whether or not you have a complete picture or not, or at least enough of at least a higher percentage, enough of the picture that you can perform the next action. And so this is also referred to as eventual consistency. But with this leads to race conditions for us. Because when we need an exact picture of what something looked like at a specific time, and we need it right away, we need it right away. Like we have to be able to choose our next steps. And so we can't just go based off partial information most of the time. So we need a canonical place to go. We want to get rid of all these ad hoc solutions. All these components in their own way are trying to figure out what the state of the system is by collecting information, storing it in memory, and then manipulating it and trying to normalize it in a way or denormalize it in whatever way it makes sense for that particular component's use of that data. But what we really need is a more canonical place to go get this important information. So when we don't have a canonical thing, what we see is we have like this kind of like, wait, what just happened kind of scenario. You receive information, you're told that there's new data available or something has happened, and then once you've received it, you then make the decision to go out and get it, and while you're going over the internets and the tubes trying to get to the data, someone else has written data out from under you. And so when you go to look at it, it doesn't look like what you would expect some of the time. You don't notice this right away in a smaller system, but as messages and more data comes to be, you start noticing that, man, this is a really big problem. And so again, you wind up trying to solve it with ad hoc solutions. And this is commonly referred to, there's an old way to describe this, which is the two generals and the messenger. And so General 1 is trying to tell General 2, he sends a messenger to General 2, through hostile territory to say, okay, we're going to attack at noon. And as he sends the messenger over, he's sitting there thinking, did he make it? It's 10 to noon. We got to attack, but I can't attack unless I know he's going to attack. So he's waiting for the messenger to come back and acknowledge that the other guy got him. And so General 2 then says, tell him okay. And then the messenger goes back. But now this guy's thinking, did he get my okay? I don't know. And so it goes back and forth, and so you really never know. So you wind up with timeouts. You're just like, well, if he doesn't show up in 5 minutes, we're just going to go ahead and do it anyway, right? But you're taking a big risk right now, right? Like you can't, I don't know if it's really, did he understand this? Are they actually going to attack with us? Like, because we can't go in by ourselves. So one way to solve this was to have temporary exchanges with RabbitMQ. We would create a temporary exchange first, and we'd send out a message with the address of the reply. And then that way it was only our reply. So we could reduce some of the traffic, but what this caused is a lot of temporary exchanges inside of RabbitMQ. If you looked at our dashboard, it would scroll for pages. It was useless because we had so many exchanges going on. And this worked pretty well for a while, and it still works today for some problems, but as a general use case, it hurts us in places. So what we need is consistency. This goes back to the canonical place to look for information. And so in order to do this, consistency is something that solves this problem. And so while what we had before was eventual consistency, which is great for a lot of problems, but not particularly good for the kinds of problems we were trying to solve. And so we need to consolidate. So we need to take all this information from all over the place, and we need everyone to report into the same place and tell us the information that they know is exact, is true. And then we can get a consistent view of what everyone else sees at any particular time. So if I go and look at this one point in time, I know that anyone else looking at that point in time sees the same thing I see. And then I know that they're going to make the right decision because they see the same thing that I see. So one way to do this is to try something like Postgres. And this leads us to having a database, like a SQL database. So the SQL database gives us consistency. And the RabbitMQ, the message queue, gives us the ability to broadcast changes in state. And so all the clients, so now we have two clients. We have a SQL client hitting the database looking for information, and once it has information or updates information, the clients will then send information to RabbitMQ so that other things don't have to pull. We don't want them having to constantly run SQL, select all from state or whatever, right? And if they keep doing that, that's not going to scale for us. I mean, we've got one master Postgres, and we just have to keep buying a bigger and bigger box, right? I mean, like, polling is going to kill us. We need to be able to tell people, okay, now go look for the data. And only the people that need to know are the ones that should be polling. But again, this leaves us race conditions. We still have the problem of the messengers, and we still have the problem of ships passing in the night, one guy writing and then telling others about it, and then someone else coming and writing, and then another guy going, and then that same guy going to read and not getting the information the original guy who sent the message wanted him to see. But that's one of the problems. But then there's the next problem is that it's a single point of failure in our system. Is that Postgres and SQL databases, they're generally one master. They have one master. That's where you write to. You can read from the slaves and you can read from the master too, but the only place you can write is to the master. So if that master goes down, we can no longer write. And if we can no longer write, then our system kind of comes to a grinding halt. If RabbitMQ goes down, if the main RabbitMQ goes down, we have to fail over, we'll lose messages, things can get out of order. It's a mess. We call it a cascading global failure sometimes, because you'll see that when one little bug exposes or something you hadn't really accounted for, and it's really, really hard to account for all the things that can go wrong in an inconsistent environment like that. But when they do go wrong, you'll notice that, oh wow, there was a little bug, and that bug just exposed 10 more bugs, which exposed 3 bugs each, which exposed other bugs, and then the whole system just goes poof. So the early days of Heroku were really fun and interesting. So we can solve that problem fairly easily. We can give the database a higher yield, or something similar. Another term that's somewhat similar to that is uptime. Most of you have probably heard of uptime. How many of you have heard of yield and know what yield is? Okay, so for those of you who don't know, yield is the probability of getting a response for a request. So if I only have one master on one machine, the probability is going to be low, not incredibly low. It depends on what kind of machine it is, what the network is, and then the topology of the system, but it's not as high as it could be if I had more than one master that I could write and read from, right? So, or I want to know that if it goes down, I can bring it back up as quickly as possible. How many of you have ever tried to recover a downed database, right? So usually what happens is you've got, in order to have redundancy on slaves, so you'll have multiple slaves, and those slaves are, slaving from the master, and all this information's like, syncing in order in a consistent fashion, so that both of them have the same thing, and the master goes down. Now the clients can no longer connect to the master, and they're stuck. They're just sitting there trying to connect back over it, and they're getting, connection refused. And so in order to save that, what you do is you promote a slave to become the new master. But in order to do that, there needs to be a human to come in and say, you're the new master. Well, when that's at 3 o'clock in the morning and you're rubbing the sleep off of your eyes and you're trying to do that, the probability of human error becomes very high, right? Like, you might make a mistake. But qualified and experienced DevOps engineers will be able to do this, half asleep, fine. But it's still, there's that time to getting to it and trying to figure out which slave is going to be the best slave to promote, which one has the most data, so forth, so on. So what if we could do this in an automated way, so that it would just automatically fail over? There's a couple of projects out there that are pretty old that try to solve this, but they require an amazing amount of black art, and it's not even science. It's like voodoo magic. But the problem is that there can only be one, right? Like, we have to make sure that there can only be one. So in order to do that, we need something with consistency and high yield, where this gives us consistency, but not the highest yield that we could possibly want. And so we could solve this problem by just putting another Postgres database down here with 2 more slaves, right? And then we could use that one to make the decision, this is going to be the new slave, and we can automate that. But what's the probability of that one being alive if this one isn't alive, right? So how can we make that decision? So we just keep pushing the single point of failure all around, and it just never seems to go away. We're trying to sweep it under the rug, but it just never seems to go away. So we needed to solve this problem. So again, consistency plus high yield. This brings me to tolerate. We need to be able to tolerate a system failing, or hardware or software failures. Maybe a bug in bug in some of our code may not have, been right, and something just sparked and went wrong, right? So we created a project called Doozer. My coworker Keith Rarick and I started on this about a year ago. How many of you have heard of Doozer yet? How many of you remember what these guys are? No? Okay. It's probably just an American thing. I don't know. Do you guys remember Fraggle Rock? No? I remember the little guys that would build things, and then the Fraggles would come over, and then they would eat their bridges, and then they would go, oh no, and then they just build it right back up, and there was just constant, back and forth between the two of them, right? Well, that's what Doozer is. He's just if he gets knocked down, he just builds it right back up again, right? But the key to this is, also, one point I want to make is that we made during the design of Doozer, we had also a very heavy emphasis on the design and the usability of Doozer itself. So let me get into Doozer. Doozer is a multi-master system. This means we have more than one master. I can make writes to any master and guarantee total order in each of them. That looks like this. If I write to this one, then if I were to read out at that level, that transaction ID, if I were to read out of that transaction ID on another one, I would get the exact same value. And if I read it from anyone, I would get the exact same value. So they both see commits in the exact same order. They're all totally ordered. And so this gives us relief. These guarantees allow us to not have to have so many ad hoc solutions anymore. We just know that what we're seeing is right. We don't have to even guess. It's just correct. And this problem is solved with Paxos. How many of you have heard of Paxos? Okay. How many of you have heard of Google's Chubby project, or how distributed consensus? Right? Okay. So Paxos is an algorithm developed by Leslie Lamport at Microsoft Research. It is a consensus algorithm. It is for many things, or many components, who are all participating in consensus over an unreliable network with unreliable processors, to come to an agreement that this is the thing that will be that, right? It's kind of hard to explain. It's very abstract, but once you've come to a decision as to what transaction 1 is going to be, then all the other masters will only ever learn that value for that transaction ID ever. It's guaranteed that they will never one of them might accidentally learn something else. So you always have that consistency. Because they're performing consensus. And again, I already explained this, but it's totally ordered. So each member of the cluster, each master, sees the same sequence of events that happen. So when I write to one, that's the order that's going to come out on all the others. So all clients can, that means that clients don't necessarily all have to be connected to the same one. They can connect to anyone at random and still see the right data that they're supposed to see. So let me talk about the data store. So the data store, it looks a lot like a Unix file system. You have directories with files. I'll show you what this looks like in a second. But right now you can only read and write whole files. There is no partial reads. There's no like seeking or anything like that in a file. It's just you get all the contents, or you send, or you write all the contents, and that's it. And what it also gives us is the data plus events about the data. How many of you know what notify is? iNotify on the Unix file system, right? So you can subscribe to events on the file system, and if someone touches a file in one directory and you happen to care about that directory, you'll get a signal from the operating system saying that file just changed. Here's what changed about it. So Doozer also has this mechanism built in. So it's a little hard to read, but Doozer ships with inside it's just one little binary, right? We wrote it in Go, so it compiles to a static little binary, and this is also important because we can just take this little binary and just kind of shove it all around, right? We can just make copies of it everywhere, and it doesn't need to be linked to any particular C library or anything. It's just all there, and there's no dependencies needed, so it can run anywhere without any, crazy setup. So here's the file system, and so what you're seeing here is this is the start. This is what Doozer looks like when it first starts. Doozer is self-configuring. There is no file system configuration file. It's all within its own data store, within its own system. It uses consensus to configure itself. So here, when you see the little yellow lines, that's the little web UI. It's subscribing to events. It's subscribing to data changing. And so here it's blinking in yellow to tell you, hey, this data changed. And so you kind of can visually watch your information. This little web thing doesn't scale very well when you have a lot of data, but it's really useful for debugging and getting started. So let me go over the design. It was designed to be easy to use, reliable, and highly focused on consensus. Other things that had consensus in them weren't really specifically for just consensus. They were kind of a smaller piece of a bigger puzzle. And so there was a lot of extra features in them that we didn't necessarily need, or we could have done without. And they were also a little more complicated than we liked, and they weren't as flexible as we liked. And so that's why we wound up creating Doozer, because we wanted to focus on just one thing, which was consensus. That is the most important part of what we wanted. Without consensus, we were back to where we were before. So we wanted to get that absolutely right, and we wanted to get you just the commands you need. So we painstakingly crafted the API for this. We needed the API to be as simple as possible. Heroku is a polyglot system. Like I said, there's like 7 languages or 6 languages that we support right now. And internally and inside Heroku, it's not just Ruby running. It's also Node.js, it's also Python, it's also C, there's all sorts of different languages. Erlang is another. There are all sorts of different languages there that are all working together. And so if we decide that we want to use a new language for another particular problem, and we need a Doozer client for it, we should be able to write that client in a matter of a few hours, not a few months, as some mailing lists have told us others take. So there's very few commands. They're all very orthogonal. Here are the simple commands: get, set, delete, and wait. So the first 3 are self-explanatory, but wait, I'm going to have to give you an example of how that works. But before I can describe that, I have to tell you, you guys are like, oh my God, just get to it. So before I can go into that, you need to understand that Doozer keeps versions. Every time a file changes, it keeps the diff. Something like how Git works, but not really. Keeps a diff, a version, in memory. And so that the new change is what you'll read if you're looking for the most recent information, but you can always go back in time, and the clients can read older information, which is really useful. I'll show you an example. But again, it's called a persistent data structure. If you Google for that and look at the Wikipedia site, you can get more information of how they work. But this is by far the coolest part of Doozer to me. No one else really does this, at least not the way we really needed it to be done for our particular purposes. So I'm going to show you using this is how you start a simple Doozer D. You run Doozer D, and you hit enter. And then that's it. You open up a new terminal window, and then you can now use the Doozer command line client for doing simple set and get operations. So here, the way the Doozer command line client works is that all the contents of the file get streamed on standard in, and then over there we say Doozer set hello 0, and that 0 is something like a compare and set token. How many of you know what compare and set is? Okay, All right, find me at the drink up later and I'll explain it to you if you really want to know. But then down here we can say doozer get hello, and you'll see that we got world, right? So, but the thing to notice here is that the 71, that's the new revision. That was the revision at which the store was at when that key was set. So now that I have that information, if I were to get hello, I'm getting the latest information. Somewhere in between here, someone else in another process could have set that thing out from under me. So by getting the latest version, I'm getting whatever was there when I asked for it, not when I set it, right? But to demonstrate how you can avoid that with doozer, well, let's print that to world. But this time, instead of 0, I'm giving it the revision, or the CAS token 71. And I'm saying, set this to this contents if and only if the revision is equal to or less than, equal to or greater than the revision of 71. So the file that it was at, so at this point you can see that it set it. So we set it at 71, and then the next command we get it at 71. So we getting it at 71, we got world, lowercase world, not capital world. But when we go and get hello at the current revision, we get world, but if we go back to 71, we get lowercase world again, right? So we can go back in time. That's that persistent data structure, get like that access to that. That's where there's a lot of power with that for a lot of the stuff that we do. And doozer also by just naturally just comes with, or a benefit of this is that you also get idempotency for most commands. This means that clients that are written that you can, require and or import into your own programs can already do all sorts of really cool things for you behind the scenes without doing anything terrible or scary, right? They can basically, if you disconnect from one master by accident and the client notices that, it can reconnect to another one for you, and without returning a value to you yet, and then reissue the commands that you already had outstanding, and then continue where you left off, and your code has no idea that even happened, but it already did it magically for you. So that's a pretty huge benefit. So when we as engineers at Heroku, we need to know that kind of stuff can happen automatically for us, because that relieves us of a lot of mental complexity and juggling all this information and complexity about the system. So here again, another quick example of how this works is that if I were to set it twice, I get 71 on the first one, and I set it with 0 again, 0 being missing, you'll get a rev mismatch. It says, no, you can't set that right now. So this is useful for locking, and I'll show you in a second. But if we do it and then we just send some arbitrarily large number to it, what'll happen is it'll say, okay, that's fine, the revision doesn't match, it's greater than, so go ahead and set it, and it'll override it. So in order to do a clobber, right, you don't send a special value -1, you just send max int. So here's one way, one common use, or one pretty good use for doozer, is things like, let's say, your varnish configurations or your Nginx configurations. So here, I'm omitting errors simply for demonstration. Error handling is, oh, and this, by the way, this is Go code. How many of you have looked at Go code or have seen Go? Okay, so, sorry, it's not Ruby. So what's happening here is I say get my app config at the most recent value. And then I'm going to update, I'm going to take the value, and I'm going to update my Nginx config. And then I'm going to go into this infinite loop, and I'm going to wait. And so this is the wait example. This is where I'm saying wait for my app.config to change after revision R+1, and R was the revision we got that configuration was last changed at that we know of, that when we started life. And then we were able to then we can update it with the event's body, and then we can set we can now grab its revision, and then loop back around and wait again. So whenever we want to update the Nginx config, and we need to keep them in unison and consistent, we simply just set that key in doozer, and then everybody gets to know about it immediately. And so with very little code, we're doing a pretty complex operation. What would normally would have taken a lot of effort using something like RabbitMQ with Postgres or something. And then this is for distributed locks. Here you can see we take the current revision, we go into an infinite loop, we then set it as if it's missing with the value as my ID, or my lock ID, whatever I want my ID to be. And then I check to make sure there's no error. If there was an error, we obtain the lock. That means that we were unable to set it. That means somebody else got it. Or no, I'm sorry, if error equals nil. then there was no error, so we got the lock, we can return out, everything's fine. But if we didn't get the lock, then wait for that lock to become available or to change, update the revision, and then try to lock it again. And then down there, unlock is as simple as just deleting the key if we want to, whenever it's time to unlock. So now we have multiple processes on multiple servers across the network can then share a lock, and they can then lock any particular thing that they would like. So some quick operational notes on Doozer. I'll wrap this up. It's a crash-only design. How many of you are familiar with like quit in Redis or in Postgres, right? Like you can send a quit. Yeah, you can't do that with Doozer. If you want Doozer to die, you have to kill it. You have to brutally murder it. You have to kill -9 it or shut the server off or shut off the network, something. There's no need for it to have graceful shutdown because it's all replicated. Everything, it's because it's based on consensus. There's no need to have any of that. It's also self-hosted configuration, as I mentioned earlier. Doozer configures itself. The really cool part about this is that we get this benefit that has been plaguing us with other technologies at Heroku, is that we can start a cluster of 3 Doozers, and if that's okay and enough, we can have 3 Doozers. That's good. But if we want more reliability or a higher yield or the higher probability of getting requests back and tolerate a region and on EC2 going down and making sure that we still have information and locks available at least somewhere else in the world that we can go to, we can grow and shrink the cluster without ever taking it down. We can simply just say, add another member, allow another member to join the cluster, so we set a key, it goes through consensus into its own configuration file, then its config is just in its own little special directory, and then it just watches itself. It uses its own client internally to be able to watch the file system. And then we can then start adding new nodes, or we can remove new nodes, or not new nodes. We can remove old nodes, add new nodes, cycle them out, upgrade the system without ever taking it down or having to hup it or anything like that. And also it keeps a tail of history. This is configurable, but this also means that when you're doing waits, you don't lose any events as long as you get to it quick enough, but usually quick enough means within the order of magnitude of days. As long as your component can reconnect within a few days, it'll see the information it was looking for. Generally it happens in nanoseconds, so it's not something that would ever probably happen. And so also it stays in memory. All the data is in memory. It doesn't persist to disk. This is kind of controversial. A lot of people debate, and I'm sure Sean's going to get up here and talk about some cool things that React does and how it persists. But for us, with Doozer, it doesn't. We didn't really think that that was as necessary as we wanted. Because if Doozer is down, because it's a multi-master system, we can spread it across the world. If Doozer went down, we're royally FUCKED'd anyway. So it really doesn't matter. We're not storing credit card information in here. We're storing like Nginx configurations and stuff like that, right? That's not what this is for. This is for configuration information, locking, all that stuff. But locks don't matter when the whole system is completely kaput anyway, right? Because nobody's reading locks because they're all dead. So it doesn't really matter. But for the cases where sometimes repopulating or reseeding the data from a backup is a good idea or is helpful, we have Mark McGranigan wrote Gorg. Gorg simply is just a client of the Doozer cluster and sees all the events coming in using the wait command and then writes a wall file out to something like S3, which can then be replayed back into Doozer. And for the future, we're working on speed. So writes are slow because whenever we need to go through consensus, we need to make sure that at least quorum agrees, quorum being half of the number of nodes over 2 + 1, that enough of those have all agreed that that's the that is going to be the information, or that's going to be the thing for that revision. And so that means that writes are slow, but reads don't go through consensus, so you can just read from any one of them. Reads will appear slow if you're looking for something in the future, because it won't send you a request back until it's learned the value of whatever key you're looking for at revision that you're looking for. And for ephemeral nodes, or what we call like ephemeral locks or ephemeral nodes or ephemeral files that will disappear with the loss of a client, the next thing we're working on is a companion tool for Doozer. This is not something we want to build into Doozer. We'll build a companion tool for it. It'll just simply be a client of Doozer. And then that is how you'll have ephemeral locks and ephemeral nodes. But again, we wanted to specifically focus on one thing inside of Doozer and have a very sharp little tool, a very lightweight, sharp tool. And then if we did it just right, then we would be able to create all of these different companion tools with it because they can just be built as normal clients. So here's some links. Thank you. Any questions, or do we have time for questions? Do I have water up here? Oh, sweet. Thank you. Yeah.
Here. I didn't quite get it.
Only 1 minute for questions.
Okay. Quick.
I didn't quite get it. What is Paxos? So, Dozer, it's an implementation of Paxos?
Correct. Yes. It uses Paxos for consensus. No matter how you try to do consensus, you wind up always with Paxos. It's just mathematically proven that that is what you wind up with. Next.
Blake, so what's your pick on the cap theorem?
That's a long debate, and we only got a minute.
Yeah, but I mean, you must have left something out. I mean, if it's consistent and...
Well, cap theorem is consistency, availability, and partition tolerance. We support a level on each, but not... If there's a severe partition and you lose quorum, writes stop. You won't get requests. Your yield isn't necessarily 0 yet. It's just you need to go shove it or poke it in the eye and bring up other nodes somewhere else and then point all the other clients back over, and then they can continue reading where they left off. But it's not as tolerant for that, but that's a rare scenario, at least as we've experienced. But for consistency, we really just needed consistency, and then availability, and the definitions of consistency, availability, and partition tolerance are like so varied that it's not something that like I can say it's like a fireside chat kind of thing, right? So if we wanted to talk about that.
Okay, thanks.
Yeah. Okay, that's it. Thank you.